we're going to look at the real-life applications of heat transfer. Let's start with conduction. So most saucepans are made from metal with plastic handles. So let's have a think about how conduction comes into that. So metal, good conductors of heat, free electrons. So those electrons, as they heat up, will move much faster and actually transfer through the metal really quickly. Plastic, an insulator. It's not made of metal, there are no free electrons, and actually the molecules do not vibrate very easily as they heat up. They're quite resistant to vibration, so the transfer of heat is much slower. Serving dishes are usually made from glass or china. So let's have a think about whether they are good insulators or good conductors. So if we have a serving dish, we don't really want to be burning our hands, so we would prefer that they are more insulating and less good conductors. Now, you can actually tell if it's a real diamond by touching the diamond to your lips. So what the jeweler is trying to tell is the difference between glass and diamond based on the conductivity. So if it was a good conductor, it would feel cold. And diamonds are good thermal conductors. Here is a fun one. Baked Alaska is a dessert with meringue on the outside and ice cream in the center, and they set fire to it. So why doesn't the fire melt the ice cream? So we need to think about what's going on in the meringue. The meringue traps lots of air. It's very light and fluffy, and air is not a good conductor. It's a gas. Conduction only happens in solids. And look at this lizard. It's doing something odd. It has flattened its body so that it is in contact with the rock. And that contact is what is allowing conduction between the hot rock touching the skin of the lizard, and the heat is transferring into the lizard, so it's warming up the lizard so the lizard can go on and do what it needs to do in the day, go off and find some food. So let's have a look at some real-life applications for convection. Here is a double-glazed window. So a piece of glass on one side and a piece of glass on another side with a very small gap in between. And that small gap could have air or may even be a vacuum. Convection has to happen in a space with gas, so if it's a vacuum, that'll stop convection and stop heat transfer, and the small gap means that actually convection currents can't set up very well because you need a big space for a circle of current. So in a sustainable house, this will help to keep the hot air on the right side of the window. Even whilst I'm sitting here, I can hear my own computer. Its fan is going. So this is called forced convection. So forced convection is actually pushing air past my hot computer, and it is taking away the hot air around my computer so that my computer chips inside it, all the electronics don't get too hot. And let's think of convection in the real world of the environment. We have cool sea breezes on a hot day because the sun is beating down on the land by radiation. The land is getting warm, and the land warms the air next to it so that air becomes less dense. As the particles spread out, the warm air rises, and in turn it's forcing the cooler air downwards. The cool air comes in to replace the hot air that's disappeared. So if you're sitting on the beach, you get a nice cool sea breeze on your face. Let's think about radiation, some everyday examples of radiation. Have you ever looked at the back of your fridge? There's a black panel on the back of your fridge. It's black because black is a good emitter of heat. So it takes the heat out of the contents of your fridge and radiates them away from the back of your fridge. Here, this young boy might be suffering from hypothermia. Maybe he got wet. He gets wrapped in a shiny silver blanket. This shiny silver blanket is actually really, really thin, and you think that's not going to keep him warm. But what it's doing is stopping radiation. If you stop radiation, the heat in that boy's body will stay there and he won't get any colder. And here we are stopping absorption of heat from the radiation from the sun, and by making the buildings white, then in those hot countries, they do not absorb heat, which is another reason in this picture why when you store petroleum or fuel in a tank, you want to paint it white or silver because you don't want the contents to be absorbing radiated heat from the sun. And look at our polar bear here. This polar bear is actually being viewed through a thermal imaging camera, and it's quite cool on its surface. It should be about 37 degrees because it's a mammal, but the surface of the bear is very cool because it has white fur, and white fur does not radiate heat very well. It traps it inside, and it actually has black skin, so any heat from the sun will be absorbed by the skin of a polar bear, but it will not radiate heat very well. And the last picture we've got here is for us to think about urban design, or the design of our towns. And you will have all had that experience on a hot day where you've had to kind of go, ooh, 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 as you run to the car, and the car park tarmac is black, and you actually almost have to walk along the white lines on the road so that you don't burn your feet. Well, if we are careful, we can design towns to be cool. So if we think about radiation, we want to have surfaces and substances and items in our streets that absorb that radiation of heat from the sun and keep us at the pavement level nice and cool. And you can see all the green trees here absorbing the sun's radiation and providing shade and keeping the streetscape nice and cool.